Okay, I'm going to start recording now. I'd like to go back to something that I just went over last week, somewhat too quickly, perhaps. That is the integral equations, how to get, I just said that one could get an integral equation. I didn't really show you how to do that. And so what I've done now is to show you how to do that. And in particular, it turns out that it's important first to write your second order ordinary differential equation in self-adjoint form. And that can always be done, as was shown in section 7.32. Then what you do after you have it in self-adjoint form is you do a sort of integration by parts and multiply by -1 and write the equation in this form. Now you can integrate. The left-hand side is a double derivative, and then on the right-hand side, you have something to integrate, and then you have a first derivative. So these terms become are very easy to integrate once, and that's all you really need to do. You integrate once, and when you actually, I'm not even sure why I'm saying that one needs to use this integral form here, because if you just integrate this thing, what you get automatically is that PU is F plus an integral KU. And what you get then is that F is this and K is that. I've made a new exercise out of that. So I actually need to change that a little bit, because the exercise isn't the same as what is said here. Okay, so to recapitulate, you take the self-adjoint form, write it like this, and then you just integrate. It's not particularly complicated. And when you integrate, you simply get this expression here. In particular, for Legendre's equation, the self-adjoint form looks like this, and we then rewrite it this way. And when we integrate, what we get, I guess maybe it is a little more complicated than I just said. Anyway, you integrate and you get 1 minus x squared Pn of x is equal to this expression here times Pn of y dy. So that's the integral form of Legendre's equation. Two instances of this are for n equals 0 and n equals 1, you get these two, and you see the first two Legendre polynomials satisfy this integral equation identically. What did I want to say beyond that? There's another thing that I was going to say in this, since we're doing Bessel functions now. Remember, I said that one thing one could do to, in general, to render differential equations easier to solve is that one can do an integral transformation. And so if you have a differential equation that looks like this, you let u equal to some integral along a contour, then you get an equation like that. And then you say, oh, I want an m such that m acting on k with w derivatives is L acting on K with Z derivatives. And then you've transformed this into that. And now you just have W derivatives here, and you can integrate by parts. So that's the trick. These integral expressions, of course, we've seen many times. Just to see it for Bessel's equation, we have, here's one form of Bessel's equation. You can write L like this. You choose K to be this expression here, and I'm just wondering why there's no space there. So I don't. Let me just. I'll just do it again. Anyway, so what you do is you pick a kernel. Now, of course, it's not obvious how to pick such a kernel. That's not the easiest thing in the world to do. Anyway, you pick a kernel that's entire in Z and W, if you can at least, and then you look for a differential operator such that M on the kernel is L on the kernel, L being this. And it turns out you can just let M equal to D2 dW squared. And then you find indeed MK is LK. And MK is just minus the second derivative of K with respect to W. And so then your original integral equation, which was, well, that doesn't look right. Well, all right, it's not. Anyway, KW, the second derivative of K with respect to W plus lambda squared KV equals 0. We then integrate by parts once and then again. And now what you've got is if V satisfies this simple harmonic equation, which I've rewritten here, and if this derivative vanishes at the endpoints of, not the derivative, if the thing inside the derivative vanishes at the endpoints of the contour, then you've got that this whole thing equals 0. And I left out the equals 0 in, so let me, in fact, put in the equals 0. I hope the book has the equals 0. So dW equals 0, dW equals 0. So that's basically how. That's the utility of these integral transformations. You start with an equation that's fairly complicated, and you wind up with an equation for something else, V, and then you rewrite your solution as a contour integral of this kernel with this simple function V. And for Bessel's equation, V is just e to the I lambda W, because e to the I lambda W has the second W derivative plus lambda squared V is 0. And so you get these expressions then for U. And then what you do is you choose the contour so that the boundary terms vanish. And in this way, one gets definitions of the first and second Hankel functions. And contour 1 goes from here, maybe I should use the, so this is 11 November. Yeah, that's when the First World War ended on the 11th hour of the 11th day of November. I guess it was what, 1918, something like that. Anyway, so this first contour, C1, goes from minus I infinity up to the origin, over to minus pi, and then up to minus pi plus I infinity. C2, on the other hand, runs from pi plus I infinity down to pi, across to 0, and then down to minus I infinity. So these contours are chosen so that the boundary terms vanish. Boundary terms being the analog of this. And because these Henkel functions then are so smooth, so analytic in Z and W, you can deform the contours, and then if you have Z and lambda both real, then one Henkel function is the complex conjugate of the other. Okay, so that's what I wanted to review from the previous chapter. I thought it was interesting, actually, that putting the differential equation in self-adjoint form made the computation of the integral equation much simpler. You might wonder, how did I find out? Well, I tried to do it.
Belgium, very good. Belgium. Yes, so the answer is C. Make sure you guys are practicing every time I say these words. Thank you. Sanjan?
Okay, I didn't understand a word of that. If that's a comment that somebody wants me to understand, please write it in chat. So we have you can write whatever you said in chat, and then I'll try to figure out what it is that you want me to do, and then I'll try to do it. But the sound from a computer through Zoom to another computer and then through my hearing aids isn't always perfect. We all have different accents. Fortunately, most of us have American accents, but as you get away from American accents to Australian accents or Scottish accent, Welsh accents, and so forth, and then you go into European, Eastern European accents and so forth. The worst case being, or some of the worst cases are the Asian countries with small populations. The problem is that if you have a small population, typically the language of a small population has a rather small number of phonemes. And so the natives of that population have real trouble learning foreign languages because they start out with a small number of phonemes. The opposite case is China and India, in which in both cases the populations are huge, the phonemes are numerous, and they can learn how to speak unaccented English pretty easily. And two counterexamples are Korea, which is a very advanced country, and Japan, another very advanced country. But in both cases, it's very hard for people from those countries to learn how to speak English without an accent. I don't know why I went on for that, but anyhow, I have completely, I'm afraid, lost track of what I was going to talk about. We were talking about Legendre polynomials, And we had gone some distance into this. No, actually, we had finished Legendre polynomials. God, I don't know what I'm doing today. We were talking about Bessel functions, and in fact, let me go to where we were. I think basically it was Bessel functions of the second kind. And what one does is one defines them this way, at least one for nu not equal to an integer, one defines them as this ratio. But as nu approaches an integer, we've got this singularity in the denominator here, or a zero in the denominator. And so what you have to do is take, in other words, when you have something that looks like, say, sine x over x, and you want to know what is that? Well, the limit of this, say x goes to 0, is the derivative of sine x, cosine x, divided by 1, the derivative of x. And you now let x go to 1, and you get 1 over 1, which is 1. And so that's the technique. This is called Lhopitals rule, and you apply it here. So you differentiate the numerator, differentiate the denominator. The derivative of the denominator is cosine pi nu, and that's -1 to the nu, or if nu goes to n, it's -1 to the n, and one gets this expression here from this ratio. There's another expression for this, which is in the book equally. I thought that this formula was slightly, or this formula, I should say, is slightly simpler than the one I did in the book, but they're both correct formulas. These Bessel functions, these y's are called Bessel functions of the second kind. They're also called Neumann functions, and they diverge as z goes to 0. For large z, as long as the imaginary part of as long as the phase of z is less than pi, so we're talking anywhere in here, but just don't close that angle down to pi. So anything except the negative real axis. So all over there, as r goes to z is r, e to the I theta, r going to infinity, you get this expression. Now, when do you need the y news, or the y's? And it's, if you're representing functions that are finite at the origin, you don't need them because they all diverge at the origin. On the other hand, if the point rho equals 0 is not part of the physical region, then you do need them in general. Bessel, and I have graphs of these. These are graphs of the y's, the first 6 y's actually. And you see them all dive down. They seem to dive all down to -infinity as rho goes to 0. And yeah, there's the minus sign. And rho is there. And so that's what happens. There are Bessel functions of the third kind. These are the Hankel functions. And I just reviewed how they're defined in terms of contour integrals. These Hankel functions, which are called Bessel functions of the third kind, you can write them as linear combinations of the ordinary Bessel function of the first kind and Bessel function of the second kind. I don't know where people get these crazy names. When z is imaginary, what you get are called modified Bessel functions. So j at ix and h1 at ix are called modified Bessel functions, and these are written as I alpha and k alpha, and their limiting forms are that they're powers of z. The i's are power of z at small z. The k's are inverse powers of z. And so they're divergent. As z goes to infinity, we get expressions like this. Simple cases are these, which are actually equalities. Note to myself, hold on, check 10 points. So we went through coaxial waveguides yesterday. So I'm going to skip that and go to Bessel functions of the first, spherical Bessel functions of the first kind. And as I said to you yesterday and the day before, because spherical symmetry is so much more symmetrical than cylindrical symmetry, the functions are much nicer. And their original definition in looks frightening. I mean, it looks as though they're going to be much worse than the ordinary integral Bessel functions. But in fact, they're not. They're very simple functions by comparison. They satisfy this differential equation. And Rayleigh developed a formula for them in terms of sine x over x and derivatives of sine x over x. And in particular, the lowest one is sine x over x. The first one, J1, is then sine x over x squared minus cosine x over x. And these are all finite at the origin. We know that Helmholtz's equation separates in spherical coordinates, and if we write an arbitrary solution in terms of a function of r, function of theta, function of phi, we get this expression here. This is a function of r, this is a function of theta, this is a function of phi. Actually, this is a function of theta and phi. No, actually, this is a function of theta. Yeah. Sorry. All right. Let me just. I don't quite remember the notation. Anyhow, we then find we said if the all values of phi are physical, then phi has to be EVIM phi. The capital theta satisfies this associated Legendre equation, and the product obeys Bessel's equation if the radial function is a spherical Bessel function. And Rayleigh's formula leads to a recursion relation, and that also leads is a way of showing that they satisfy Bessel's equation, his differential equation. What we know about the Bessel functions is that they go as rho to a power for small rho, a power divided by a square root of rho. And so this goes as rho to the L plus a half divided by the square root of L. So that winds up being just rho to the L. For large rho, what we do is we just notice that J1 by Rayleigh's formula is this derivative. And what does it give us? It's cosine rho over rho plus sine rho over rho squared. So you see, the sines and cosines are all between -1 and +1, but whenever the derivative acts on the rho in the denominator, we get a 1 over rho squared. So these at large rho are irrelevant. And so JL of rho at large rho is just -1 to the L. All the derivatives of rho act on the sine, and the rho's cancel except for one of them. And so it's approximately rho to the minus L pi over 2 divided by rho. I mean, this is an approximation, of course. If we go to this example, we can see that the solid curve is J1 and the approximations are, this is the approximation for small rho, and this is the approximation for big rho. And you see the big rho approximation is terrible to small rho, and the small rho approximation is terrible to big rho. But the small rho approximation is very good at small rho, and the big rho approximation is actually pretty good when rho is about 3. And it becomes excellent when it's, say, 10. So where were we here? The spherical function, Bessel function satisfied the self-adjoint Sturm-Liouville equation. So this is the self-adjoint form. And with an eigenvalue k squared, weight function rho is equal to r squared. The eigenfunctions vanish at r equals a and form an orthogonal basis in this way for a self-adjoint system on the interval 0 to a. And since the eigenvalues go to infinity as n squared or as L squared, depending on the point of view, these eigenfunctions are complete in the mean, and one has this delta function expansion, and one can expand any function that vanishes at r equals a and also at the origin in this way. And these then are the coefficients. Now on an infinite interval, it turns out that the orthogonality relation looks like this. Whoops. Orthogonality relation looks like this. And in fact, there's another way of thinking about it. You can think about it as an integral over k instead of r, because after all, it's JL of kr. And so in fact, going from here to here is just sort of, it's sort of a card trick with the letters K and R. There's also a trick that's worth knowing, which is actually due to Schwinger. The trick is that 1 over z dz on this integral from -1 to 1 of e to the I zx dx turns out to be 1/2 the integral from -1 to 1 of x squared minus 1 e to the I zx. Well, I mean, this was, of course, known probably by Leibniz, but what Schwinger did with it is to show that, or to notice that you could iterate it and get this expression. And more importantly, he showed that if you use this expression and this formula for J0, one could write Rayleigh's formula for the spherical Bessel function, which involves this ratio and therefore this integral as a derivative of that integral. Then you use Schwinger's trick to get this, and then you integrate by parts. In other words, the z to the L is just L derivatives with respect to x of this phase. And so now we have the spherical Bessel function as this integral, and you might say, gee, that's worse, much worse than Rayleigh's formula. But you can now integrate L times by parts and shove the derivatives onto the polynomial. Then you use Rodriguez's formula and you get PL of x. So this is then the final formula that the spherical Bessel function of z is a kind of Fourier transform of the Legendre polynomial, which is frankly surprising, but true. What people do with that is they set z equal to kr, x equal cosine theta, and get this expression. And then they're able to write e to the I kr cosine theta, expand that in terms of cosine thetas. We're thinking of this as a function of theta. And now this coefficient is essentially a spherical Bessel function. And so now e to the I kr cosine theta, well, that's e to the I k dot r. And the PL of cosine theta, you remember, is by the addition theorem, is a sum of y stars. And so you get this equation, which is used in quantum mechanics for scattering theory. And so in a quantum mechanics class, what happens is the professor or the book just throws that at you, and you just have to swallow it without actually understanding it. Now, I'm not sure how much to do this. Maybe I'll do this example. Spherical Bessel functions occur in the wave functions of free particles with well-defined angular momentum. So the Hamiltonian for a free particle, of course, p squared over 2m. We're talking non-relativistically. If we have L squared, the angular momentum operator, and so forth, then we can have eigenstates of all of these things. KLM then is an eigenstate of magnitude of momentum, of angular momentum, z component of angular momentum. And then the inner product of that state with R is then, you can then show that that's equal to a spherical Bessel function times a spherical harmonic. And these in turn, if we integrate over the complete sets of R states, we by doing R squared dr d omega, what we get is this expression, and these two are delta of L prime M prime, and these guys give you a delta of KK prime. So these states are, as you'd expect, orthogonal because they are eigenstates of three different, each state is an eigenstate of three Hermitian operators, and the eigenvalue is different than they're orthogonal. The completeness relation looks like this. The inner products with an eigenstate of free momentum, a free particle momentum P prime look like this. And one can then use the previous formula for e to the I k prime dot r to write it like this. If you go to, we talked about about how the Bessel functions are at small values of their arguments. They're basically as r prime to the L, or kr to the L if you want. And I don't know why I switched from r prime to r here. So let me just look at that. You could have a prime here and a prime there. In any event, you get kr to the 2l plus 3. And so that's very small unless, I mean, even when L is equal to 0, this is very small unless kr is small. I'm sorry, yeah, unless kr is small. If kr is small, then of course, what am I saying here? This, if you have big L and tiny k, low momentum, then this is small. What do I want to say? Small for big R is what I want to say. But as you let R go to infinity, it grows as far as I can tell. So Well, the point is that R is always very small because we're talking about a potential that is, it either falls off as 1 over R or it falls off exponentially. If it falls off very rapidly, like exponentially, then for a short range potential, this P of R is going to be essentially 0 unless L is 0. And physicists came upon such things in a big way about 100 years ago when they were studying nuclear physics for the first time. And they were scattering low energy hadrons, say protons, off nuclei. Then apart from the electromagnetic effect, the effect of the strong interaction, the scattering off the nuclear force, was always an S wave at low energies, and S wave meaning L equals 0. And so then they realized the nuclear force had to be of short range. So I've sort of said this backwards. If the potential is of short range, and at big R, the radial wave function looks like that of a free particle, and you can then compute the the phase shift in this way. And when you study phase shifts in quantum mechanics, you see that the sum of the sine squares of the phase shifts gives you the total cross section. I'm not sure how much to do here. I tell you what, I'll skip this, but I'll be happy to do this on Wednesday of next week. Or maybe I should do it now. Okay, so a quantum dot is, or at least some quantum dots are cadmium, selenium spheres less than 2 nanometers in radius. And laser photons can excite electron hole pairs in them, and they fluoresce for 10 to the minus 9 seconds or so. And we can imagine that this is that the potential for the electron that's been ionized, that's been kicked out of an atom by the laser beam, that this rattles around the 2 nanometer cadmium selenium sphere essentially freely, but it can't get out, and because of an electrostatic effect. And so what you've got is a wave function that looks like this, namely it's 0 for R greater than A. It's a spherical harmonic, a spherical Bessel function, because inside the sphere, the potential is, let us say, 0, infinity outside the sphere. So this is actually the exact solution then. And these zeros give the energy eigen values. And the reason for that is that the Hamiltonian, of course, is p squared over 2m, v being 0, acting on psi. And this, if we imagine that it's an S state for J0, for L equals 0, then the J0 is, the ZLNs are 0n, and they're n pi. And so this is essentially n pi, and then there's a 1 over a squared. And if you put the units in, you have an h bar squared as well. And then you have to divide by 2m. And so I go through some of the arithmetic here. If you're curious, you can follow it without my help. Then there are spherical Bessel functions of the second kind, and these are again given by Rayleigh's formula, very nice formula in terms of cosine rho over rho, and that tells you then that they're singular as R goes to 0. And the first two are minus cosine rho over rho, and this expression essentially 1 over rho squared. And the dominant term is, for large rho, is again one where all the derivatives act on the cosine. So it's something like this. Small rho, it's rho to the minus L minus 1. They're all infinite at short distances. So here's y1 and y2. These are their approximations. This is a little technical, so I'm going to skip this. If you really, really, really want it, I will try to do it for on Wednesday. So I'm going to say a few words about group theory, because we won't or probably won't be offering 467. I'm going to tell you the things that I really, really think everybody needs to know about group. Every physicist needs to know about group theory. First of all, what is a group? It's a bunch of elements and an operation that is technically called multiplication and often is a kind of multiplication. And the properties are the product of any two elements is in the group or in the set. It's their associative, so FGH is FGH. There's an identities element E, such that GE or EG is just G. And every element of the group has an inverse, and GG inverse is E, or G inverse G is also E. Okay. Now, the reason why group theory is relevant to physics is that physical transformations naturally form groups. And why do they form groups? Well, suppose the elements of a group are all physical transformations on a given set of objects that leave invariant some property of the set of objects. They might be points in the XY plane. The property could be the distance from the origin. The physical transformations that leave unchanged these distances are rotations about the origin. And more generally, if you have a bunch of transformations that change objects in a way that leaves some property of the objects invariant, then if T and T prime both leave the objects invariant, then if you do first T and then T prime, the objects are still invariant. The property is still invariant. And so the thing is closed. Associativity is automatic because that's just what we mean by doing transformations one after the other. The identity transformation is don't do anything. The inverse is undo what you did. And so physical transformations naturally form a group. Examples are the group of rotations, group of reflections. There's also a group of permutations. You have n objects and you order them, you just change the order. If the order of multiplication, if GH is the same thing as HG, then we say the G and H commute. If all the elements of a group commute, the group is said to be abelian, named after this guy, Niels Abel. Examples are orthogonal groups. They are real matrices that leave in real matrices in n dimensions, n by n matrices that leave points that when they move the point, the distance of the point from the origin remains the same. So they're rotations in n dimensions. If you require, and that's the group ON. And if you say, well, we want just to consider all rotations, n-dimensional rotations in n dimensions, but only ones that don't have reflections. So we want the determinant to be 1, then we call that SON. And so the strict group of rotations as opposed to rotations and reflections is SO3. Unitary groups are n by n matrices that are complex, and they leave this quadratic form invariant. And SU2 is, for example, a rotation group for spin 1/2 particles. The group SU3 is the symmetry group of the strong interactions. And I say this with somewhat tongue in cheek, because we can't do the calculations of these strong interactions because they're strong. And although at very high energy, they become weak, and we can do perturbation theory at high, for high energy scattering. But these, at low energies, these are nonlinear, infinite dimensional, differential equations. And so they're just so far hopeless. Some people think that that one can unify the, well, I'm going to skip that. The symplectic group, the set of all 2n by 2n real matrices that leave invariant the commutation relations of quantum mechanics, that's the symplectic group, SP2NR. By the way, I haven't seen this in the literature. I came upon it, but it must be there in the literature somewhere. I just haven't seen it. The number of elements in a group is the order of the group, and a finite group is a group with a finite number of elements. And examples are Z2, which is the group, the parity group, whose elements are just the numbers 1 and -1. Z3 is basically, I guess, e to the I 2 pi over 3, e to the I 4 pi over 3, and the number 1, I think. Some infinite groups depend continuously on a set of parameters. They're called continuous groups or Lie groups. A group is said to be compact if the squared norm, a trace of the squared norm or the trace of d dagger d is bounded for all. Here I'm thinking of matrices in the group. SON, ON, SUN, UN, these are all continuous Lie groups of infinite order, and they're compact because they're either orthogonal or unitary. There are non-compact groups, and in particular, the Lorentz, the group of translations is non-compact. The group of Lorentz transformations is non-compact because you can accelerate a moment. When you accelerate a particle, it's the coordinates can get arbitrarily big, or the fall momentum can get arbitrarily big. If you have a group, now this is an important concept, you might be able to do the following. You might be able to find square matrices for each element of the group such that when you multiply the matrices, you get the same matrix that represents the group elements that's the product of F and G. So D of F, D meaning, it's actually from a German word, Darstellung, meaning representation. Anyway, the representation, the matrix that represents the group element F times the matrix that represents the group element G has to be the matrix that represents the group element FG. If you can do that, then you have a representation of the group. And if the Ds are unitary, then you have a unitary representation of the group. And such things are used a great deal in physics. For example, the rotations for a spin 1/2 object are group elements of SU2. And here we have the representation of the rotation group in terms of 3 by 3 matrices. And one simple fact about representations is it's good to know is that compact groups possess finite dimensional unitary representations. And that fits in very nicely with quantum mechanics. On the other hand, non-compact groups possess infinite dimensional unitary representations, but not finite dimensional unitary representations. So something about symmetry in quantum mechanics. suppose, first of all, definition of a symmetry transformation, sort of an abstract definition. It's a map of states. Psi goes to psi prime, phi goes to phi prime, that preserves probabilities. So the probability of the system psi being measured to be in the state phi is the absolute value squared of the inner product. If that's the same as the probability of psi prime being found to be phi prime, then we say that this transformation, this map G, is a symmetry. And what Wigner showed a long time ago, and apparently Weinberg found a sort of gap in Wigner's derivation and filled it in his the first of his 3 books on quantum field theory. But anyway, what the 2 of them showed is that the action of a group of symmetry transformations on the Hilbert space of a quantum field of quantum theory can be represented either by operators that are unitary and linear, and that's the normal case. So momentum, rotations, so on and so forth. These are translations, rotations, and so forth, Lorentz transformations, and then the transformations of particle physics and so forth. These are all typically linear and unitary. That's the usual case. But the other possibility that is mathematically allowed is transformations that are antilinear and anti-unitary. These are transformations that I find just a bit spooky. Whenever I have to deal with an antilinear, anti-unitary transformation, I get a little bit nervous and I have to look very carefully at what I'm doing. But for practical purposes, the only case in which we have antilinear, anti-unitary transformations is the case of time reversal. And in fact, when you think about it, time reversal is, not something that we know how to do. What we have is we can do a rotation, we can do we can do the various other transformations. Well, I don't know about all the ones of particle physics, but certainly the translations and the rotations and the Lorentz transformations, all of which are part of the Poincare group. We can do all of those physically, but this time reversal, we can't go back in time. I mean, if we could go back to 1929 after the crash, buy the United States for a few $1 million, and now, or maybe $1 billion, I don't know what it would have gone for, and then sell at present day values, and one would be enormously wealthy. Anyway, let me just see what other stuff is in this transformation, because I'm not going to spend an enormous amount of time on this chapter. Maybe I'll jump to YangMills' theory just to show you that this is actually pretty simple. So the idea is that the action or the Lagrangian of a YangMills theory is unchanged when a space-time dependent unitary matrix, and those are typically written this way. Theta is just a number. Or theta A, that's a bunch of real numbers that depend upon space-time. The TAs are Hermitian matrices. And if you act on the fields, these fields are have several components, and this matrix, if this matrix is n by n, then this is an n-dimensional vector psi. Psi prime is an n-dimensional vector. This is an n by n matrix. It's obvious that since U is unitary, by the way, U is unit, let me just mention why that's the case. Here we've got U is e to the I h. H dagger is equal to h. And so U dagger is e to the minus I h dagger. But if h is Hermitian, this is e to the minus I h. And so U dagger U is e to the I h, e to the minus I h, and that's equal to 1. So that's why these things are unitary. And because they're unitary, U dagger U is 1. And so this inner product of this n vector with that, the complex conjugate of that n vector is invariant. What Yang and Mills did was show why it is that one can also make derivative terms invariant. And what they effectively did was generalize electrodynamics. Although Einstein had actually done something equivalent, but more subtle and more sophisticated in general relativity with his covariant derivatives. But anyway, so they replaced ordinary derivative by covariant derivatives, and the covariant derivative is an ordinary derivative plus a matrix. And this matrix is I times a Hermitian operator. And what they did was then they said, well, we want this covariant derivative to transform like the field. So the covariant derivative transforms, so there's a prime, and the field transform is the same thing as the unitary operator acting on the covariant derivative times the untransformed field. Well, what you've got here then is, you see this derivative acts on the U. That's what causes the problem. So you have diu. You also have U di on psi, and then you have ai prime on U. And that all has to equal this. And so if you solve for ai prime, you can see that it's just equal to this. And so this is how the A's are matrices. Remember, the A's looked like this. In other words, here, well, there I say AI is minus I, TAA. This minus sign is, I probably should have left out. So this is an n by n matrix, n by n unitary matrix, a derivative, and so forth. So this is how the gauge fields transform. In electrodynamics, what you have is you have A prime mu, for example, is A mu minus d mu of lambda, where we say this is a scalar function. And when this happens, a charged field transforms by something like IQ, I'll put in a plus or minus to IQ lambda. So the fields transform as e to the IQ lambda, charged fields, and the electromagnetic field transforms as a derivative. That's that gets generalized when the group goes from just, see, the electromagnetism is a group U1, which is just 1 by 1 unitary matrices, which is to say just things like e to the I theta is an arbitrary element of U1. The Faraday tensor is the commutator of two covariant derivatives. If you imagine that these were not matrices, but just numbers, then this term vanishes, and this is just F mu nu in electrodynamics. So let's see. I'm not sure what else to do there. I don't want to make things impossible for you. Maybe I'll spend a little time, the rest of the hour, talking a little bit about special relativity. I assume you all know about special relativity. It's the basic idea is that, once again, you want something to remain invariant. And so you consider transformations that of the x's that leave these things invariant. Or equivalently, transformations of, say, x and y, where these are both 4 vectors that leave that such that x dot y prime, by which I mean the vector part dotted into the vector part minus x0, y0, all primed, is equal to x dot y, which again is just x dot y minus x0, y0. So the transformations x prime equals L of x and y prime equals L of y, L on y. These being 4x4 matrices, these leave these inner products invariant, and consequently these guys form a group, and the group is the Lorentz group, obviously. And examples of these transformations, I'll get back to that if I don't forget. Examples of these transformations are, for example, let me write cosh as CH of theta, SH of theta, SH of theta, CH of theta, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So these are these. So this is an L, a Lorentz transformation in the x direction or xt direction. And of course, if some of you may have noticed that you could have a Lorentz transformation that's 4x4, but doesn't do anything to time at all. And so it leaves the time parts. Let me see if I can get, in other words, you could leave the time parts completely invariant and just change the space. Well, those would be rotations and reflections. So the Lorentz group is made up of rotations and, of course, translations. Actually, I'm a little concerned about what I just said about translation. Rotations for sure. I'm not sure about translations. Let's say x plus a dot y plus a. No, this is not equal to x dot y. All right, so forget translations. But rotations, reflections, and ordinary Lorentz transformations. And this is sort of the archetypical Lorentz transformation. These are often stated in terms of a matrix that's called the Minkowski space metric. It's written as eta very often, and it's -1, 1, 1, 1, with zeros everywhere else. And this can be thought of as, we can call this eta ik, ik going from 0 to 3. The thing about this is that eta, by the way, eta upper ik turns out to be the same as ordinary eta ik. So eta ik, eta kl, this turns out to be just delta lk. As you might expect, if you multiply these two guys together, you get, minus 1, 1, 1, 1, minus 1, 1, 1. Obviously, you're going to get 1, 1, 1. There is this annoying minus sign in special relativity. And the way I deal with it, and a lot of people do it this way, is they use upper indices upper industries have no hidden minus signs. But lower indices do. And in special relativity, the only time components have hidden minus signs. So for example, the fall momentum is energy, actually literally energy over c times the 3 vector of momentum. So this is the fall momentum. And these are, in other words, P upper 0 is E over C, and P1 is, it's P1 and so forth and so on. But you could equally write that as P lower 1. And on the other hand, if you do have lower indices, then P lower 0 is minus P upper 0 in special relativity. So that's what you have. So then you can say the inner product, for example, of x dot y, you can say that this is x I, y I. And what does that buy you? Well, for I equals 0, you have x0, y0. And then for the spatial parts, you just obviously have x dot y. But this x0 has a hidden minus sign. So this is x0, y0 with a minus sign plus x dot y. So the thing that's invariant is a sum with one lower index and one identical upper index. That summed gives you something that's invariant. Let's see, we haven't had a question. There's a chat box here. You can say something, you can write, or you could say something. Let me get, so what? Well, an important thing is when 2 points are space-like. So if you have x minus y squared in the sense of x minus y dot x minus y. And so this is x minus y vector dot x minus y minus x0 minus y0 squared. So this is the separation between 2 points. This is the invariant separation. I say invariant because this is unchanged under Lorentz transformations. So that means that this is a separation that looks the same to all observers, again, all inertial observers in special relativity. And there are 3 possibilities here. If a light signal can go from X to Y, then X minus Y squared in this Lorentz invariant sense is equal to 0. If, on the other hand, you can send a particle, a massive particle, from X to Y, then what you've got is X minus Y squared. There better be more time than space. And so this is negative, and this is said to be time-like. If, on the other hand, you just can't send anything between X and Y, because X minus Y squared is positive, this means that the space part dominates, and this is, wow. Boy, oh boy, what is this? Space line. Oh, Jesus Christ. I really do need to, so this is, Jesus Christ. All right, somebody who knows something about more than I do. This is space-like. All right, let me maybe take this eraser and try. I can't erase that. Oh my God, we just. All right, so now I'm back where I'm back in the thing, and I guess I can write. I think I better end. This will be the last lecture on this particular scroll. So this is space. This is getting to be pretty annoying here. What? Well, or maybe space-like. All right, I think I'm going to give up writing on this for the moment. We're almost out. Now, what's remarkable here is that suppose they are space-like, then delta S squared is said to be the proper distance. Here I've got P and Q as opposed to X and Y. I think X and Y make more sense. Anyways, space-like events occur at the same time in some Lorentz frames. So the coordinates of P and Q could be 0 and CTL with CT divided by L less than 1. And so you can arrange with a particular Lorentz transformation, you can arrange for to go to a frame in which these two guys, since if they're space-like, in which in a certain frame, not a unique frame, but in a certain set of frames, these occur at the same time. Time-like is a case where in some Lorentz frames, two events that are time-like occur at the same place in some Lorentz frames. And light-like are ones that can be connected by a light ray, which is what I just went through saying here. Now, in special relativity, this thing that's invariant, of course, is space squared minus time squared times c squared. Sometimes inadvertently, I set c equal to 1 because people doing particle physics or relativity, general or cosmology, very often just set c equal to 1 so as not to have to keep writing it. The proper time is the time in the rest frame of the moving object. And that proper time is then ds squared. And if we have lab time of t, then the proper time is the ds squared, whereas we would think of this thing as moving in the lab and with a speed v, and we would say that ds squared was 1 minus v squared over c squared dt squared. But the people moving would say, no, this is my time squared. And the result is that, okay, I'll get to the question. The result is that the proper time is always less than the lab time. Okay, difference between proper time. Proper time is the time experienced by the moving object. Conformal time, let me see. Offhand, I don't recall what conformal time is. I could really quickly Google it. So there are conformal transformations that leave certain things invariant. And there's also a all right, well, one definition, but I've never seen this definition before. So this is, you can think of conformal time as the amount of time it would take a photon to travel from where we are to the farthest observable distance, or equivalently, how long it took a photon to come from the farthest observable distance to get to us. I wrote a pedagogical paper on cosmology, and I think there's a link to it, or a link to a PDF of it on the class website. If you're interested in cosmology, I'd recommend my pedagogical paper on that. All right, well, I'm going to stop it now unless there's one further question. No. All right, so I wish you all